The final type of numerical integral that we're going to do is called a trapezoid sum. And the deal is that we notice with left sums and right sums using rectangles that they commit quite a bit of error. They can overestimate or underestimate depending on the shape of the function. And we corrected for that by using midpoint sums. So there was some overestimate and underestimate canceling each other out partially. But an even better way to do it is to just slice into trapezoids. So if I visualize one of these trapezoids just blown up really large, I can see that I can get a really good match for the area under the curve by just joining 2 points on the curve to make this simple trapezoid. I will remind you real quick that the area of a trapezoid is just given by the average of the two heights on the left and right sides multiplied by the width. Now let's take a look at what the trapezoid slices look like if we slice into n trapezoids. Okay, here's our trapezoid sum. And I can see that these match up to the curve so well that it's hard to tell that I've even sliced this into these simple quadrilaterals. They're just matched up so well to the curve. So this is an excellent way of approximating an integral. And we actually use this in the physics lab quite a bit. So let's try to get a formula for the trapezoid approximation on a to b for this function. I would start out by saying that a is going to be called x0 and b is going to be called xn. I get an expression for the width of each subinterval, and that's b minus a divided by n. I then get an expression for the cut points, the xi's. So there's x0, x1, x2, x3, and so on. So my ith cut point is going to be my starting point plus I steps to the right. Okay, then I can write down my approximate area, and I'm going to do this in expanded form. And the area of my first trapezoid is going to be the average of the heights at the left and right sides of the subinterval. So I'm going to have 1/2 f of x0 plus f of x1, and then multiply by the width. I do this all the way along my trapezoid approximation until I get to the last trapezoid. And the right-hand side of that is xn, so the height of the right-hand side is xn, and the left-hand side would be xn minus 1. So I have the average of the height at the left side plus height at the right side times the width. Now I can write this in summation notation. And I have n of these things. I'm going to start at I equals 1 and go all the way to n. And I have to make sure my indices are correct to match up with what I have in expanded form. So I'm going to have an f of x0 should be my starting point. Well, that means if I'm plugging in I equals 1, I'm going to have to write this as x sub I minus 1. So I get an x0 out of that. The next height would be one step to the right at xi. So I can see that my heights work out correctly for the first rectangle. I don't want to forget my delta x here. And then I'm going to check on the last rectangle. If I plug in I equals n, then I'm going to end up with an f of x sub n minus 1 and an f of x sub n here. So the last one works. And now I've got a general formula for a trapezoid sum. Let's apply this to this simple function e to the negative x squared. And the reason I chose this, again, is because it has no symbolic antiderivative. So if you want an area under this curve, you always have to use a numerical approximation. And I want the n equals 10 trapezoid sum for this function on the interval 0 to 1. And it looks something like this. And once again, the trapezoid approximation is so accurate that it's hard to even tell from the picture that I've built this out of trapezoids. It looks like I just sliced the curved area into slices. But these are actually quadrilaterals, so their tops are straight. It's just they're lined up with the function so close you can't even tell. Let's go ahead and label our cut points. That's x0, x1, x2, and so on. And I've sliced into 10 of these things, so my last one is going to be x10. We get an expression for the width of each subinterval. That's just the total interval width divided by the number of slices, and that's 1/10. Then we want an expression for the ith cut point, and that's the starting point plus I steps to the right. Plugging in delta x equals 1/10, I get I/10 for that. And then I want to write the area in expanded form one more time. This just helps to get things right. And the area of a trapezoid is the average of the heights. So my first one, I would take the height at the left end of the subinterval plus the height at the right end of the subinterval and divide by 2 out in front and then multiply by the width. And then my last one would be 1/2. And here's an x10, which means this is an x9 right here. F of x9 plus f of x10 multiplied by the interval width. And then I write it in summation notation. We have 10 things to add up, so my index is going to go from 1 to 10. And when I plug in I equals 1, I've got to start with an x0 here, so that guy is going to have a subscript of I minus 1. The next one is going to have a subscript of I times delta x, and then I double check real quick that I get the first and last ones correct. So when I plug in I equals 1, I get f of x0 plus f of x1 over 2, so that's what I have here. When I plug in I equals 10, I get f of x9 plus f of x10. So everything checks out, and we're ready to actually plug this in. So when I apply it to my actual function, e to the negative x squared, I'm going to get a 1/2. And then I have f of xi minus 1. Well, that would be I minus 1 over 10. So I have e to the negative I minus 1 over 10 squared plus e to the negative, so this is going to be f of xi. Xi is I over 10, so I have I over 10 squared. And then delta x is a 1/10. Now I'm going to head to my computer algebra system and plug all of this stuff in to get my approximation. Okay, we're here in Maxima, and I'm using the sum command to add everything up. And I put a 1/20 out in front because that's the combination of the 1/10 and the 1/2. And there I have %e, that's the special symbol for e, to the negative quantity I minus 1 over 10 all squared. That looks good, plus %e to the negative I over 10 all squared as I goes from 1 to 10. So I'm going to hit Shift Enter on that, and I get an approximation of 0.7462 and a bunch of additional decimal points. I'm just going to round to the thousandths place and say it's 0.746. The final step I'm going to do here is to check against the built-in numerical integration algorithm in Maxima, and that's called quad QAG. So I've set it up so it says quad QAG %e to the negative x squared. So it's our original function formula as x goes from 0 to 1. And then I put in the number 4, and that's just my choice of the numerical integration algorithm to apply to this integral. There are 6 different algorithms, numbers 1 through 6, and they're all so accurate it doesn't really make a difference for our purposes. I'm going to hit Shift Enter, and I get 0.7468, so it'll round to 0.747. So I can see that our trapezoid approximation is good out to the thousandths place where it only missed by 1 digit.